Hello and welcome to my talk about the optimal L1 approximation of the log-Heston SDE by Euler-Type methods. This is joint work with Andreas Neumkirch from the University of Mannheim. We start with the well-known Heston model, which was developed by Heston in 1993. It models an asset price, or in this version here, a log asset price, which is denoted by xt, and its stochastic volatility Vt, which is modeled by the CAR process. So you can see the two SDEs of the Heston model here. Let me say something about the parameters. We have V0 and X0, which are the two starting values of the processes. Kappa is the speed of mean reversion of the volatility process. Theta is the long-run mean of the volatility process. Sigma is the volatility of the CAR process. R is something like the risk-free interest rate. And rho is a correlation parameter. Furthermore, we have two independent Brownian motions, W and B. Here you can see the Feller index, which is denoted by nu. It's 2 kappa theta divided by sigma squared. By the Feller test, we know that the CAR process is strictly positive if the Feller index is larger than 1. If the Feller index is smaller or equal to 1, the process can reach 0 with a positive probability. And our topic of interest is now the strong approximation of the CAR process and the full Heston model by Euler-Type methods at discrete points. A naive Euler scheme for the CAR process is not well defined. As you can see here, one step of this scheme is normally distributed with these parameters. So after just one step, the scheme can become negative, which causes trouble with the square root here. Therefore, a well-defined Euler scheme for the CAR process requires a fix. In the literature, there exist several fixes, such as the partial truncation, high MMAU, the symmetrization, full truncation Euler, and so on. As an example, we are showing the partial truncation Euler here. We are taking the positive part of the scheme under the square root, and therefore the scheme is well defined. So how does the partial truncation Euler work for the full Heston model? Let's note first that we use an equidistant discretization, as you can see here, where tk equals k times delta. And delta is t over n. N is the total number of steps that we are making. For the log price process, we use the standard Euler scheme, but note that we only plug in the positive parts of Vtk here. The L1 error for the CAR process and its discretization, as well as for the full Heston model and its discretization, is stated here. Now we would like to know if we can find a decay rate in the number of steps n. In the literature, there exist several articles that analyze the strong convergence of discretization schemes for the CAR process. In earlier papers, strong convergence without a polynomial rate was proven for several schemes, which also include some of the before presented Euler schemes. A lot of research was carried out for the so-called drift implicit square root Euler scheme, which first appeared in a paper by Alfonsi in 2005. In his article from 2013, a convergence order of 1 for a Feller index bigger than 2 is established for the L1 approximation. The article by Hefter and Herzwurm was a breakthrough for the case where nu was smaller or equal to 1. Here they looked at the truncated Milstein scheme for the CAR process and proved an L1 convergence order of nu in this parameter range. Also, the best possible L1 approximation for the CAR process at a single time point was analyzed. It turns out that we have min of nu and 1 as the best possible rate. Therefore, the truncated Milstein is optimal for nu less or equal to 1, and the drift implicit square root Euler is optimal for nu larger than 2. There are not that many results for Euler-Type methods which prove strong convergence with a rate. We have two papers by Bossi Diop and Berkawi Bossi and Diop. In the last one, they prove LP convergence of order 1/2 for the symmetrized Euler under a very strong assumption on the Feller index. In this paper, they also proved the statement for a more general drift. Kosma and Reisinger proved an LP convergence order of 1/2 for the full truncation Euler scheme, where P lies in the range of 2 and nu minus 1. They also assumed that the Feller index nu has to be larger than 3. There are several other works concerning the strong approximation of the CAR or more general processes, which are listed here. Now we present our first result. Under the assumption that nu is larger than 1, we are able to prove an L1 convergence order of 1/2 minus epsilon, where epsilon can be chosen arbitrarily small, for both the full Heston model and its discretization and the CAR process and its discretization. The special thing about our result is that it holds for all kinds of Euler-type methods, which turn the standard Euler into a well-defined scheme, as I presented before. So this includes the symmetrized Euler, the absorbed Euler, the fully truncated Euler, the Hayamawa Euler, and so on. Our proof relies on the Ito-Tanaka formula and an estimate of the local time of the error process. For a Feller index lower than 1, our approach yields a convergence order of nu-1/2. However, simulation studies indicate that the sharp rate should be minimum of nu and 1/2. Our next result deals with the best possible L1 convergence rate of an equidistant discretization of the full Heston model, as you can see here. For nu larger than 1, we can prove that this best possible rate is 1/2. So our convergence rate from before of order 1/2 is optimal for the full Heston model. Our proof reduces the approximation problem to the optimal L1 approximation of the Levy area. And we use a symmetrization argument as in Jensen, Müller-Gronbach, and Jaroslav-Zewa from 2016. Now let me summarize what we have shown. We proved an L1 convergence order of 1/2 minus epsilon for Euler-type methods for the log-Heston model and for the CAR process for nu larger than 1. Furthermore, we have shown that the L1 convergence order 1/2 is the best possible rate for schemes that rely on a equidistant discretization of the Brownian motions W and B for nu bigger than 1. The case nu less or equal to 1 still remains an open question. As I said before, we could prove a convergence rate of nu-1/2, but this does not seem to be sharp. Also, we would like to extend our result to more general processes such as the CEV process. This is the end of my talk. I would like to thank you very much for your attention.